All right. Hello, class. Mr. Pettibone here. I am recording a lesson for the week of April 26th for AP Physics 1. So we are still reviewing for the AP exam. Okay? And so for that reason, this lesson is going to be a review of circular motion and gravitation. All right. So I am going to start. Oh, and by the way, this corresponds to Experimental Physics Quiz 5. So I'm going to go ahead and start by talking about circular motion. Okay. So circular motion, you have an object that is moving in a circle. So it's going in a circle of radius r. With speed v. Okay. So I'm going to just draw a top view of this circle. So we're watching the circle. It's going around like this. Like so. So there's some object going around. The radius of that circle is r. And so what we learned is that at any point on the circle, your velocity points tangent to the circle. So the velocity is tangent no matter where you are on the circle. Okay. The velocity is always going to be tangent. And then the acceleration, which is called the centripetal acceleration, you're not accelerating because you're speeding up or slowing down. You're accelerating because the direction is changing. And in the case of circular motion, that acceleration points in towards the center. Okay? Now, we also have Newton's second law, which says that F equals ma. So we can see F net equals ma. So we can see that the force and the acceleration are linearly related to each other. And so if the acceleration points towards the center of the circle, then the force also points towards the center of the circle. Okay? So that's called the centripetal force. The force that is pointing towards the center, that is making you go in a circle, is called the centripetal force. So notice how this force has to change directions as you travel around the circle, because depending on where you are, the direction to the center changes. Okay? So we learned a couple of equations. Okay? One of the equations is for the speed if you're moving in a circle. And speed is distance over time. So the distance traveled is 2 pi r, because that's the circumference of a circle. And then the time to complete that is called the period. So 2 pi r over the period is your speed. Okay? This isn't velocity because velocity has direction as well. And then there is an equation for the acceleration while you're moving in a circle. It's called the centripetal acceleration. And the formula for centripetal acceleration is speed squared divided by the radius of the circle. This can also be written as 4 pi squared r over period squared. Okay, so these two options both give the same answer. It's just they're expressed in terms of different things. Okay, so you get this form by plugging in 2 pi r over period for the speed. Okay. And then, of course, just like always, Newton's second law is valid. So the centripetal force is going to be equal to ma, which is going to be mv squared over r, or because the acceleration is v squared over r, or it could be m times 4 pi squared r over period squared. All right. Come on, Hazel, you can do it. Come on, baby. The door is like partially open and Hazel is trying to get it. Come on, Hazel, you can do it. Come here, girl. Come here, girl. Oh, Bug's gonna go help her. Come on, Hazel. Oh, now she lost interest. Okay, so there's a problem that I wanted to talk about that I didn't go over when I was doing my, when we learned about circular motion for the first time. And that is what's called the conical pendulum. Okay, so this is an experiment that is very common. If we were going to do an experiment for circular motion, this would probably be the one. Okay, because it's really tough to do circular motion experiments. So a conical pendulum, if you look at it sort of from the side, it looks like this. So you have a ceiling, all right, and then you have a string that has a length L, all right, and then you have a pendulum bob at the end of the string. It has a mass M, and it's going around in a circle. Okay, so here's the center of it. So this is a horizontal circle that we're kind of viewing slightly from above the circle. So it's going around like this. Like that. Okay. And so basically, you push the pendulum bob and it starts to move in a horizontal circle. Okay. When I say a horizontal circle, I mean moving like this. Okay, a vertical circle is like a Ferris wheel. Horizontal circle, it's like doing donuts in a dirt field or in some dirt or something like that. Okay, and so yeah, so we just want to figure out what is the period. All right. How are the various variables related? So one of the important variables for a conical pendulum, I guess this would be more of a 3D view because we're kind of looking at it from an angle. But one of the important variables is the angle that the string makes with the vertical. Okay? And what we can see is that the radius of the circle is not equal to the length of the string, because this is the radius of the circle right here, from the center of the circle to the edge. That's the radius. So we can see that there's a right triangle here, and the length of the string is the hypotenuse of that triangle. So, and I can see that the radius is opposite the angle. So what I have is that R is L sine of theta. Okay, so the radius is not the same thing as the length of the string. They're related to each other, but they're not the same. If I were to draw this from a side view, well, let me just continue with the 3D a little bit longer. So the acceleration always points towards the center of the circle. So if we think about the direction to the center of the circle, it's going to be like that. Like so. Okay. So the acceleration, no matter where it is, points towards the center of the circle. So what if I decided to draw this from a side view? Okay. If you're looking at a circle from the side, it just looks like a, it just looks like an edge. Okay. So what you would see is you would just see the circle, the particle going back and forth. Okay. Because it's circling out towards the camera. And then here's the ceiling, and there's the string that goes out here. And then this would be the angle theta. All right. So what if we were to draw a free body diagram on the mass at this particular moment when the mass is right here? Okay. So if I were to draw that free body diagram, there's only two forces acting on the mass. Okay. All right. There is the force of gravity, which is mg. We're having our morning dog interactions. Morning doggy interactions. So it has the weight force, mg, going straight down, and then it has the force from the rope going up at an angle. So the force from a rope is called tension. So you have tension going up in this direction. Okay, and that's it. Now, because of the angle of the string, we know that the tension, okay, is also making an angle theta with the vertical. Okay, so anytime we have a diagonal force, as I've told you before, we want to take that diagonal force and break it up into components using trigonometry. Okay, so we have the angle, so this would be f sub t sine of theta. This would be f sub t cosine of theta. So I am going to redraw my free body diagram, this time with all of the forces being vertical or horizontal. Okay, so here is the horizontal part of the tension. Here is the vertical part of the tension. All right. So now we need to apply